Well, my name is Marcus Gazadalan. I sometimes go by the handle Gazadalan, which is my last name. And I'm joined here by my coworker, Amy, who's also a good friend and longtime collaborator. We work for a company called RET2 Systems. RET2 is best known publicly for its security research and development. Behind the scenes, we do consulting and have been pushing to improve the availability of security education and specialized security training, as well as raising awareness and sharing information like you're going to see today. So this talk has been structured roughly to show our approach in breaking some of the world's most hardened consumer software. In particular, we're going to talk about one of the 0 days that we produced at RET2 in 2018. And over the course of the talk, we hope to break some common misconceptions about the process of 0-day engineering. We're going to highlight some of the observations that we've gathered and built up about this industry and this trade over the course of many years now. And we're going to try to offer some advice on how to get started doing this kind of work as an individual. So we're calling this talk a non-technical commentary about the process of 0-day engineering. At times, it may seem like we are stating the obvious, but the point is to show that there's less magic behind the curtain than most of you spectators probably realize. So let's talk about Pwn2Own 2018. For those that don't know, Pwn2Own is an industry-level security competition organized annually by Trend Micro's 0-day initiative. Pwn2Own invites the top security researchers from around the world to showcase 0-day exploits against high-value software targets such as premier web browsers, operating systems, and virtualization solutions such as Hyper-V, VMware, VirtualBox, Xen, whatever. So at RET2, we thought it'd be fun to play in Pwn2Own this year. Specifically, we wanted to target the competition's browser category. We chose to attack Apple's Safari web browser on macOS because it was new, it was mysterious, but also to avoid any prior conflicts of interest. And so for this competition, we ended up developing a type of 0-day known typically as a single-click RCE or Safari remote, kind of as some industry language. So what this means is that we could gain remote root-level access to your MacBook should you click a single malicious link of ours. That's kind of terrifying. A lot of you might feel like you're very prone to not clicking malicious links or not getting spearphished, but it's so easy. Maybe you're in a coffee shop. Maybe I just man in the middle of your connection. It's a pretty scary world. So this is actually a picture that we took on stage at Pwn2Own 2018, directly following our exploit attempt. This is actually Joshua Smith from ZDI holding the competition machine after our exploit had landed, unfortunately a little bit too late. But the payload at the end of our exploit would pop Apple's calculator app and a root shell on the victim machine. This is usually used to demonstrate code execution. So for fun, we also made the payload change the desktop's background to the RET2 logo. So that's what you're seeing there. So what makes this 0-day a fun case study is that we had virtually no prior experience with Safari or macOS going into this event. We literally didn't even have a single MacBook in the office. We actually had to go out and buy one. And so as a result, you get to see how we as expert researchers approach new and unknown software targets. So I promised that this was a non-technical talk, which is mostly true. That's because we actually published all the nitty-gritty details for the entire exploit chain as a verbose 6-part blog series on our blog this past summer. It's hard to make highly technical talks fun and accessible to all audiences, so we've reserved much of the truly technical stuff for you to read at your own leisure. It's not a prerequisite for this talk, so don't feel bad if you haven't read those. So with that in mind, we're ready to introduce you to the very first step of what we're calling the layman's guide to 0-day engineering. At the start of this talk, I said we'd be attacking some of the most high-value and well-protected consumer software. This is no joke, right? This is a high-stakes game. So before any of you even think about looking at code or searching for vulnerabilities in these products, you need to set some expectations about what you're going to be up against. And so this is a picture of you. You might be a security expert, a software engineer, or even just an enthusiast. But through some odd twist of self-loathing, you find yourself interested in 0 days and the desire to break some high-impact software like a web browser. But it's important to recognize that you're looking to defy some of the largest, most successful organizations of our generation. These types of companies have every interest in securing their products and building trust with consumers. These vendors have steadily been growing their investments in software and device security, and that trend will only continue. You see cybersecurity in the headlines every day, hacking, these systems compromised. It's only getting more popular. There's more money than ever in this space. So this is a beautiful mountain peak that represents your mission of, I want to craft a zero-day. But your ascent up this mountain is not going to be an easy task. As an individual, the odds are not really in your favor. This game is sort of a free-for-all, and everyone is at each other's throats. So in one corner is the vendor, who might as well have infinite money and infinite experience. In another corner is the rest of the security research community, fellow enthusiasts, other threat actors. So all of you are going to be fighting over the same terrain, which is the code. This is unforgiving terrain in and of itself, but the vendor has home field advantage. So these obstacles are not fun, but it's only going to get worse for you. Newcomers often don't prepare themselves for understanding what kind of timescales they should expect when working on these types of projects. So for those of you who are familiar with the capture the flag circuit, these competitions usually are time boxed from 36 to 48 hours. Normally they're over a weekend. We came out of that circuit. We love the sport. We still play. But how long does it take to develop a zero-day? Well, it can vary a lot. Sometimes you get really lucky. I have seen someone produce a Chrome/V8 bug in 2 days. Other times, it's taken 2 weeks. Sometimes it takes a month. But sometimes it can actually take a lot longer to study and exploit new targets. You need to be thinking, you need to be looking at time in these kind of scales. And so it could take 3.5 months. It could take maybe even 6 months for some targets. The fact of the matter is that it's almost impossible to tell how long the process is going to take you. And so unlike a CTF challenge, there's no upper bound to this process of zero-day engineering. There's no guarantee that the exploitable bugs you need to make a zero-day even exist in the software you're targeting. You also don't always know what you're looking for, and you're working on projects that are many order magnitudes larger than any sort of educational resource. We're talking millions of lines of code, where your average CTF challenge might be a couple hundred lines of C at most. So I can already see the terror and self-doubt in some of your eyes, but I really want to stress that you shouldn't be too hard on yourself about this stuff. As a novice, you need to keep these caveats in mind and accept that failure is not unlikely in the journey. All right? So please check this box before watching the rest of the talk. So having built some psychological foundation for the task at hand, the next step in the layman's guide is what we call reconnaissance. So this is kind of a goofy slide, but yes, even Metasploit reminds you to start out doing recon. So with regard to zero-day engineering, discovering vulnerabilities against large-scale software can be an absolutely overwhelming experience. Like that mountain, it's like, where do I start? What foothill do I go up? Like, where do I even go from there? So to overcome this, it's vital to build foundational knowledge about the target. It's also one of the least glamorous parts of the zero-day development process, and it's often skipped by many. You don't see any of the other speakers really talking about this so much. You don't see blog posts where people are like, I Googled for 8 hours about Apple Safari before writing a zero-day for it. So you want to aggregate and review all existing research related to your target. This is super, super important. So how do we do our recon? Well, the simple answer is Google everything. This is literally us Googling something. And what we do is we go through, and we click, and we download, and we bookmark every single thing for about 5 pages. And you see all those buttons that you never click at the bottom of Google? All the things are, here's related searches you might want to look at. You should definitely click all of those. You should also go through at least 4 or 5 pages and keep downloading and saving everything that looks remotely relevant. So you just keep doing this over and over and over again. And you just Google and Google and Google everything that you think could possibly be related. And the idea is, you just want to grab all of this information. You want to understand everything you can about this target. Even if it's not Apple Safari specific, I mean, look into V8, look into Chrome, look into Opera, look into Chakra, look into whatever you want. So the goal is to build up a security literature, a library of security literature related to your target and its ecosystem. And then I want you to read all of it. But I don't want you, don't force yourself to understand everything in your stack of new literature. The point of this exercise is to build additional context about the software, its architecture, and its security track record. By the end of the reconnaissance phase, you should aim to be able to answer these kind of questions about your target. What is the purpose of the software? How is it architected? Can anyone describe what WebKit's architecture is to me? What are its major components? Is there a sandbox around it? How do you debug it? How do the developers debug it? Are there any tips and tricks? Are there special flags? What does its security track record look like? Does it have historically vulnerable components? Is there existing write-ups, exploits, or research in it, etc.? All right, we're through reconnaissance. Step 2 is going to be target selection. So there's actually a few different names that you could maybe call this. Technically, we're targeting Apple Safari, but you want to try and narrow your scope. And so what we're looking at here is a tree map visualization of the WebKit source. So Apple Safari web browser is actually built on top of the WebKit framework, which is essentially a browser engine. This is open source. And so, yeah, this is a tree map visualization of the source directory where files are sorted in by size. So each of those boxes is essentially a file. Well, all the gray boxes, the big gray boxes, are directories. All the sub-squares are files. And each file is sized based on its lines of code. The blue hues represent approximate maximum cyclomatic complexity detected in each source file. And you might be getting flashbacks back to that picture of that mountain peak. How do you even start to hunt for security vulnerabilities in a product or code base of this size? 3 million lines of code. I've maybe written like 100,000 lines of C or C++ in my life, let alone read or reviewed 3 million. So the short answer to breaking this problem down is that you need to reduce your scope of evaluation and focus on depth over breadth. And this is most critical when attacking extremely well picked over targets. Maybe you're probing an IoT device. You can probably just sneeze at that thing and you're going to find vulnerabilities. But you're fighting on a very different landscape here. And so you need to be very detailed with your review. So reduce your scope. Our reconnaissance and past experience with exploiting browsers has led us to focus on WebKit's JavaScript engine, highlighted up here in orange. So bugs in JS engines, when it comes to browsers, are generally regarded as extremely powerful bugs. But they're also few and far between, and they're kind of becoming more rare. As more of you are looking for bugs, more people are colliding, they're dying quicker. And so, anyway, let's try to reduce our scope. So we reduced our scope from 3 million down to 350,000 lines of code. Here we'll zoom into that orange. So now we're looking at the JavaScript directory, specifically the JavaScript core directory. So this is a JavaScript engine within WebKit as used by Safari on Mac OS. And specifically to further reduce our scope, we chose to focus on the highest level interface of the JavaScript core, which is the runtime folder. So this contains code that's almost one-for-one mappings to JavaScript objects and methods in the interpreter. So, for example, array.reverse or concat or whatever. It's very close to what you JavaScript authors are familiar with. And so this is what the runtime folder looks like at approximately 70,000 lines of code. When we were spinning up for Pwn, we said, OK, we are going to find a bug in this directory in one of these files, and we're not going to leave it until we have walked away with something. So if we take a step back now, this is what we started with, and this is what we've done. We've reduced our scope. So it helps illustrates this whittling process. It was almost a little bit arbitrary. Previously, there's been a lot of bugs in the runtime directory, but it's really been cleaned up the past few years. So anyway, this is what we chose for our RCE. So having spent a number of years going back and forth between attacking and defending, I've come to recognize that bad components do not get good fast. Usually, researchers are able to hammer away at these components for years before they reach some level of acceptable security. So to escape Safari Sandbox, we simply looked at the security trends covered during the reconnaissance phase. So this observation, historically bad components will often take years to improve, means that we chose to look at Windows Server. And so for those that don't know, Windows Server is a root-level system service that runs on Mac OS. Our research turned up a trail of ugly bugs from essentially the Windows Server, which is accessible to the Safari sandbox. And in particular, when we were doing our research, we were looking at ZDI's website, and you can just search all their advisories that they've disclosed. And in particular, in 2016, there was over 10 plus vulnerabilities reported to ZDI that were used as sandbox escapes or privilege escalation style issues. And so these are only vulnerabilities that were reported to ZDI. If you look in 2017, there is 4, all again used for the same purpose. I think all of these were actually probably used at Pwn both years. And then in 2018, there was just 1. And so this is 3 years, over the span of 3 years, where people were hitting the same exact component, and Apple or researchers around the world could have been watching or listening and finding bugs and fighting over this land right here. And so it's pretty interesting. I mean, that gives some perspective. The fact of the matter is that it's hard to write. It's really hard for bad components to improve quickly. Nobody wants to try and sit down and rewrite bad code, and vendors are terrified, absolutely terrified, of shipping regressions. Most vendors will only patch or modify old bad code only when they absolutely must. For example, when a vulnerability is reported to them. And so, as listed on this slide, there's a number of reasons why a certain module or component has a terrible security track record. Just try to keep in mind that's usually a good place to look for more bugs. So if you see a waterfall of bugs this year in some component, like WASM or JIT, maybe you should be looking there, right? Because that might be good for a few more years. All right. Step 3. So after all this talk, we're finally getting to a point where we can start probing and exploring the code base in greater depth. This step is all about bug hunting. So as an individual researcher or a small organization, the hardest part of the zero-day engineering process is usually discovering an exploited vulnerability. That's just kind of from our perspective. This can maybe vary from person to person. But we don't have $100 million to spend on fuzzers, for example. And so we literally have one MacBook, right? And so it's kind of like looking for a needle in a haystack. We're also well-versed in the exploitation process itself. And so those end up being a little bit more formulaic for ourselves. So there are 2 core strategies for finding exploitable vulnerabilities. There's a lot of pros and cons to both of these approaches, but I don't want to spend too much time talking about their strengths or weaknesses. So they're all listed here. The short summary is that fuzzing is the main go-to strategy for many security enthusiasts. Some of the key perks is that it's scalable and almost always yields results. And so, spoiler alert, but later in this talk, you're going to see we fuzz both of our bugs, both the bugs that we use for our full chain, and it's 2018. These things are still falling out with some very trivial means. OK, so source review is the other main strategy. Source review is often much harder for novices, but it can produce some high-quality bugs when performed diligently. If you're looking to just get into this stuff, I would say start real simple. Start with fuzzing and see how far you get. So yeah, for the purpose of this talk, we're mostly going to focus on fuzzing. This is a picture from the dashboard of a simple, scalable fuzzing harness we built for JavaScript core. This is when we were ramping up for Pwn and trying to build our chain. It was a grammar-based JavaScript fuzzer based on Mozilla's Dharma. There is nothing fancy about it. This is a snippet of what some of its output looked like. We had only started building it out when we actually found the exploitable vulnerability that we ended up using. So we haven't really played with this much since then. But it shows kind of how easy it was to get where we needed to go. So something like we like to stress heavily to the folks who fuzz is that it really must be treated as a science for these competitive targets. Guys, I know code coverage isn't the best metric, but you absolutely must use some form of introspection to quantify the progress and reach of your fuzzing. Please don't just fuzz blindly. So our fuzzer would generate web-based code coverage reports of our grammars every 15 minutes or so. This allowed us to quickly iterate upon our fuzzer, helping it generate more interesting, complex test cases. A good target is 60% code coverage, so you can see that in the upper right-hand corner. That's kind of what we were shooting for. Again, it really varies from target to target. This was also just us focusing on the runtime folder, if you see in the upper left-hand corner. And so something that we've observed, again, over many targets and exotic targets, is that bugs almost always fall out of what we call the hard-fought final coverage percentages. And so what this means is you might work for a while trying to build up your coverage, trying to build a good set of test cases or grammars for fuzzing. And then you'll hit that 60% and you'll be like, okay, what am I missing now? Like everyone gets to 60%, let's say. But then once you start inching a little bit further is when you start finding a lot of bugs. And so, for example, we'll pull up code and we'll be like, why did we not hit those blocks up there? Why are those gray blocks? Why did we never hit those in our millions of test cases? And we'll go find that that's some weird edge case or some unoptimized condition or something like that. And we will modify our test cases to hit that code. Other times we'll actually sit down, pull it up on our projector, and talk through some of that code. And we'll be like, what the hell is going on there? And so this is actually, it's funny, this is actually a live photo that I took during our pwn-to-own hunt. As cliche as this picture is of hackers standing in front of like a dark screen in a dark room, this was absolutely real. We were just reading some code, and so it's good to rubber ducky among coworkers and to hash out ideas, help confirm theories or discard them. And so yeah, this kind of leads us to the next piece of advice. Is when you're doing source review, so this applies to both debugging or assessing kind of those corner cases and whatnot. If you're ever unsure about the code that you're reading, you absolutely should be using debuggers on dynamic analysis. So as painful as it can maybe be to set up JavaScript core or debug this massive C++ application that's dumping these massive call stacks that are 100 deep, you need to learn those tools, or you're never going to be able to understand the amount of context necessary for some of these bugs and complex code. So, for example, one of our blog posts makes extensive use of RR to reverse or to root cause the vulnerability that we ended up exploiting. It was a race condition in the garbage collector, totally wild bug. I said there was probably 3 people on Earth that could have spotted this bug through source review. It required immense knowledge of code base, in my opinion, to be able to recognize this as a vulnerability. We found it through fuzzing. We had to root cause it using time travel debugging, Mozilla's RR, which is an amazing project. And so yeah, absolutely use debuggers. This is an example of a call stack again. Just using a debugger to dump the call stack from a function that you're auditing can give you an insane amount of context as to how that function is used, what kind of data it's operating it on, maybe which kind of areas of the code base it's called from. You're not actually supposed to be able to read the slide, but it's a backtrace from GDB that is 40 or 50 call stacks deep. All right. So there's this huge misconception by novices that new code is inherently more secure and that vulnerabilities are only being removed from code bases, not added. This is almost patently false. And this is something that I've observed over the course of several years, countless targets, code from all sorts of vendors. And there's this really great blog post put out by Ivan from GPZ this past fall. And in this blog post, he basically, so 1 year ago, he fuzzed WebKit using his fuzzer called D'Amato. He found a bunch of vulnerabilities, he reported them, and then he open sourced the fuzzer. But then this fall, he downloaded his fuzzer, ran it again with little to no changes, just to get things up and running. And then he found another 8+ exploitable use after free vulnerabilities. So what's really amazing about this is when you look at these last 2 columns that I've highlighted in red, virtually all the bugs he found had been introduced or regressed in the past 12 months. So yes, new vulnerabilities get introduced every single day. So the biggest reason new code is considered harmful is simply that it's not had years to sit in market. This means it hasn't had time to mature. It hasn't been tested exhaustively like the rest of the code base. As soon as that developer pushes it, whenever it hits release, whenever it hits stable, That's when you have a billion users pounding at it, let's say on Chrome. I don't know how big that user base is, but it's massive. And that's 1,000 users around the world just using the browser who are effectively fuzzing it just by browsing the web. And so, of course, you're going to manifest interesting conditions that will cover things that are not in your test cases in unit testing. So yeah, it's not uncommon. The second point down here is that it's not uncommon for new code to break assumptions made elsewhere in the code base. And this is also actually extremely common. The complexity of these code bases can be absolutely insane, and it can be extremely hard to tell if, let's say, some new code that Joe Schmo, the new developer, adds breaks some paradigm held by, let's say, the previous owner of the code base. He maybe doesn't understand it as well. Maybe it could be an expert developer who just made a mistake. It's super common. Another piece of advice. This should be a no-brainer for bug hunting, but novices often grow impatient and start hopping around between code and functions and getting lost or trying to chase use after freeze or bug classes without really truly understanding what they're looking for. So a great starting point is always identify the sources of user input or the way that you can interface with a program, and then just follow the data. Follow it down. What functions parse it? What manipulates your data? What reads it? What writes to it? Just keep it simple. And so when we're looking for our sandbox escapes, we knew we were looking at Windows Server, and our research had showed that there's all these functions. We didn't know anything about Mac, but we read this blog post from Keen that was like, oh, there's all these functions that you can send data to in Windows Server. And apparently there's about 600, and there are all these functions prefixed with __x. And so these 600 endpoints will parse and operate upon data that we send to them. And so to draw a rough diagram, there's essentially this big red data tube from the Safari sandbox to the Windows Server system service. This tube can deliver arbitrary data that we control to all those 600 endpoints. We immediately thought, let's just try to man in the middle this data pipe so that we can see what's going on. And so that's exactly what we did. We just hooked up Frida to it, another open source DBI. It's on GitHub. It's pretty cool. And we were able to stream all the messages flowing over this pipe. So we could see all this data just being sent into the Windows Server from all sorts of applications, actually. Everything on Mac OS talks to this. The Windows Server is responsible for drawing all your windows on the desktop, your mouse clicks, your whatever. It's kind of like Explorer.exe on Windows. So we see all this data coming through. We see all these crazy messages, all these unique message formats, all these data buffers that it's sending in. And this was just begging to be fuzzed. And so we said, OK, let's fuzz it. And I remember we were getting all hype. And I distinctly remember thinking, maybe we can jerry-rig AFL into the Windows Server. Or let's mutate these buffers with Radamsa. Or why don't we just try flipping some bits? And so that's what we did. And so Halvar actually had a very timely tweet just a few weeks back that echoed this exact experience. He said that looking at my security/vulnerability research career, my biggest mistakes were almost always trying to be too clever. Success hides behind what is the dumbest thing that could possibly work. The takeaway here is that you should always start simple and iterate. So this is our fuzz farm. It's a single 13-inch MacBook Pro. I don't know if this video is actually going to work. It's not a big deal if it doesn't. I'm only going to play a few seconds of it. So this is me literally placing my wallet on the Enter key. And you can see this box popping up. And we're fuzzing. Our fuzzer is running now and flipping bits in the messages. And the screen is changing colors. You're going to start seeing the boxes freaking out. It's going all over the place. This is because the bits are being flipped. It's corrupting stuff. It's changing the messages. Normally, this little box is supposed to show your password hint. But the thing is, by holding the Enter key on the lock screen, all this traffic was being generated to the Windows Server. And every time the Windows Server crashed, you know where it brings you? It brings you right back to your lock screen. So we had this awesome fuzzing setup by just holding the Enter key. Yeah. And we lovingly titled that picture "Advanced Persistent Threat" in our blog. So this is a crash that we got out of the fuzzer. This occurred very quickly, actually. This was probably within the first 24 hours. So we found a ton of crashes. We didn't even explore all of them. There's probably a few still sitting on our server. But there's lots of null derefs, lots of garbage, but then this one stood out in particular. So anytime you see this thing up here that says exe bad access with a big number up there, address equals blah, 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 that's a really bad place to be. And so this is a bug that we ended up using at Pwn to perform our sandbox escape. If you want to read about it, again, it's on the blog. We're not going to go too deep into it here. So maybe some of you have seen the InfoSuck comic. It's all about how people trying to do these really cool, clever things. People can get too caught up trying to inject so much science and technology into these problems that they often miss the forest for the trees. And so, here we are in the second panel. We just wrote this really crappy little fuzzer, and we found our bug pretty quickly. And this guy's really upset. So, which brings us to the misconception that only expert researchers with blank tools can find bugs. And so you can fill in the blank with whatever you want. It can be cutting-edge tools, state-of-the-art, state-sponsored, magic bullet. This is not true. There are very few secrets. So the next observation, you should be very wary of any bugs that you find quickly. A good mantra is that an easy-to-find bug is just as easily found by others. And so what this means is that soon after our blog post went out, so actually at Pwn 2018, we actually knew we had collided with Fluorescence, one of the other competitors. We both struggled with exploiting this issue. It was a difficult bug to exploit. And we had some very creative exploit. It was very strange. But there was some discussion after the fact on Twitter by Ned, started by Ned. He's probably out here actually speaking tomorrow. You guys should go see his talk about the Chrome IPC. That should be really good. But there was some discussion on Twitter that Ned had started, and Nicholas, who's also here, said, well, at least 3 teams found it separately. So at least us, Fluorescence, and Nicholas had found this bug. And we were all at Pwn. So you can think how many people out there might have also found this. There's probably at least a few. How many people actually tried to weaponize this thing? Maybe not many. It was kind of a difficult bug. And so there are probably at least a few other researchers who are aware of this bug. So that kind of closes the, if you found a bug very quickly, especially with fuzzing, you can almost guarantee that someone else has found it.